Hello and welcome back to the time series Econometrics. In the previous lecture, we have seen random walk model. We have explained random walk model with drift and without drift, and we have seen both the types of random walk model we can basically create by summing up the error terms. Now, these error terms are white noise and their IID. They're independent and identically distributed. Now, when I have the white noise which are IID and they're basically stationary, when they add up, we get some time series which are random walk is not stationary. The question is why, if we add all these stationary error terms, they're leading to a non-stationary time series. To answer this question, if you see the how the error terms are adding up to the value in different time point is actually because is what is happening is the previous error term is also being captured in the present time, right? So that is why they are not really independent. When I take the value at tth time or t plus 1th time, the t plus 1th time value is actually capturing the error term of tth time, right? So the error terms are not really independent when I actually add them up in and to make a to make a random walk model. So that is basically the reason why we do not have a stationary process when we have the random walk model. Now, what to do with that when we have such kind of model? And in fact, in practice, you will see it is very difficult in real time. It is very difficult to get absolutely stationary process in time series. And in most of the cases, there will be some dependence. And the dependence will mostly be in terms of the previous period value. And that is why we need to adopt some other measures to actually explain, to explain how we can achieve stationarity, okay? And one such method is called differencing. Now, what is differencing and why it is important? I'm just going to explain that. But let me first write down the equation that we have been using all throughout when I talk about a random walk model, right? So I write yt equal to, say I take a with drift model, alpha plus yt minus 1 plus some epsilon t, okay? Now, if I do the differencing, so differencing is basically, you can simply assume that you can actually subtract the previous time period value from the present time period value, which means I can simply do yt minus yt minus 1 equal to alpha plus et. Now here you see the moment you do that, what is happening here is you are actually free of the yt term, okay? So yt minus 1 term. So it is no longer depending on the previous time period value. So it is now independent, right? It is not depending on the previous time period value. And that is the beauty of differencing, okay? Now differencing can be different types. So here the differencing that I have done, it is called lag 1 differencing because I have simply subtracted the value of the previous time period. So I have taken only one lag. So let me just write down. This is called lag 1 differencing. Lag 1 differencing. ENC differencing. Okay, so this is called lag 1 differencing. Uh, so essentially, what happens in most of the time series that we're going to that we'll see, the most of the in most of the cases, the value of tth time is basically influenced by the value of t minus 1th time. So, and the moment I subtract t minus 1th time value, I actually make my series free of the uh, previous free of the uh, other dependencies or free of the previous period values, right? So that is why we take these differences. Now, It can be, we can also have lag M differencing, which is basically you do it for seasonality adjustment. So this one is basically for trend adjustment. This is for trend adjustment, where I say that the moment I subtract the previous period value, I actually make my data free of any trend. Okay, so that is why it is called trend adjustment. But there could be seasonality also, right? In my data, there could be seasonality also. And when I have seasonality, what I do is I actually take a lag M difference. Lag M differencing. So for example, you take particularly for say weather, okay? So if you want to see temperature, so of course it will vary in every 12 months. So if you subtract the value from the previous value 12-month value of the weather which you had 12 months before, you actually adjust the seasonality part. Okay, so this is for seasonality adjustment. Seasonality adjustment. All right. We can do both. We can take both lag 1 differences as well as lag M differences. We call it double differencing, and double differencing is done to basically remove both trend and seasonality. Okay. Now this is very important concept in time series modeling, because as I said, in most of the cases you will have some sort of trend, you will have dependence of the values in time series, and they mostly depend on the previous period value. Of course, it can depend on more than one period value. You can take lag 2 differences, you can take lag 3 differences, and we're going to see the applications of that. And using this idea of differencing, we can actually see how we can get this trend of seasonality time series, and which we can use for further mathematical purposes. One last point is that we actually have uh, this differencing concept is important, and we're going to actually see for different types of trends, like we just in this case we have just assumed that yt is dependent on yt minus 1, but there could be other aspects of this trend, and we're just going to see some different types of trend. And in the next lecture we are going to talk about um, stochastic trend and deterministic trend, and we'll talk about these different types of trend and how to adjust these trends. Okay, how to basically detrend. The whole process is called, when I get rid of a trend, we call it detrending. Okay, so we are going to see the next lecture how we can do detrending when I have trend, different types of trend in my data. Okay, so thank you very much. We'll talk about it in the next lecture.